This is the video for section 4.1.1, initial value problems and boundary value problems. So in this section, we're going to be continuing our study of linear differential equations, but we're going to look at higher order differential equations. So an nth order linear initial value problem is of the form a sub n of x times the nth derivative of y with respect to x plus a sub n minus 1 of x times the n minus first derivative of y with respect to x plus etc. plus a naught of x times y equals g of x. And our initial conditions are of the form y of x naught equals y naught, y prime of x naught equals y1, and so on and so forth up until y of n minus, the n minus first derivative of y at x naught is y sub n minus 1. So notice here the main differences is just that we have a higher order potentially differential equation, and the number of initial conditions that I need to specify changes depending on the order of the differential equation. So just as we did in the first order case, we have an existence and uniqueness theorem for nth order linear differential equations. So we're going to assume that we have a differential equation as on the previous slide, so an nth order linear initial value problem, and we're going to let all of my coefficient functions and g of x, so the right-hand side, quote unquote, we're going to let all of them be continuous on an interval I containing x naught. Remember, x naught was my initial condition. That was where I was given my initial conditions. And if the highest order coefficient, a sub n of x, is not 0 for all x in the interval I, then the solution to the initial value problem exists and is unique. Now, reading this, you might say, well, that seems like a lot less technical and maybe even easier to check than our existence and uniqueness theorem for first order differential equations. And the thing to remember about that is that that held for any first order differential equation. So that's why it, by necessity, had to be a little bit more technical. This existence and uniqueness theorem is only holding for linear differential equations. So that's why it appears to be simpler. And we'll talk more about that in class. Okay, so first example. Let's consider the differential equation y double prime minus 3y prime minus 4y equals 0 with initial conditions y of 0 equals 1 and y prime of 0 equals 2. This is a second order linear differential equation. Since it's second order, I have to give you two initial conditions. So you can check that the solution is given by 3/5 e to the 4x plus 2/5 e to the negative x. That's a perfectly valid, well-defined solution on the whole real line. We'll learn how to solve these later, but just for now you can check that that is a solution. And we'd like to know, is this the only solution to this initial value problem? Is this solution unique? So we need to check both criteria in the existence and uniqueness theorem. So the first thing, are my coefficient functions and my right-hand side continuous on the interval of solution, or continuous in this case on the whole real line? Well, a sub 2 is equal to 1, a sub 1 is equal to negative 3, a naught is negative 4, and g is 0. Those are just constant functions, so certainly they're continuous. So the answer to this question is yes. The next question is a sub 2 of x non-zero on my interval from negative infinity to infinity. And since a2 is equal to 1, which is not equal to 0, the answer to this question is also yes. So my solution is unique by the existence and uniqueness theorem. For a second example, let's let our differential equation be x times y double prime minus y prime equals 0. And let's let my initial conditions be y of 0 equals 0 and y prime of 0 equals 0. And you can check that this has a solution, y equals c times x squared, and that solution holds for all c and r. So we've seen things like this before. That means if I have a one parameter family of solutions to an initial value problem, that means I don't have uniqueness to this initial value problem. So I have existence because I just gave you a solution, but it's not unique. So let's see if we can figure out what went wrong. So the first question, are all of my coefficient functions and my right-hand side continuous on the interval from negative infinity to infinity? Why that interval? Well, that's the interval where my solution is well-defined. And the answer is yes, the a sub 2 is equal to x, a sub 1 is negative 1, and the other two are 0. So those are perfectly continuous functions everywhere. But notice here that on any interval containing 0, and 0 is my initial condition, so the x value for my initial condition, on any interval containing that point, a sub 2 of x is also 0. So we violate the second criteria of the existence and uniqueness theorem, and so we're not guaranteed uniqueness. And here in this example, in fact, we clearly do not have uniqueness. So that's what you need to do in order to check existence and uniqueness for a nth order linear differential equation. You should read in your book about boundary value problems. They're related to initial value problems, but they're slightly different, and unfortunately we do not have such a convenient existence and uniqueness theorems for that class of differential equations.